¿Está listo? ¿El otro lado? ¿Cómo conecto con esto? ¿Cómo? Sí, vale. Thank you everybody for your attendance. It's a pleasure for me to introduce Begoña Vitoriano. She's Associate Professor at the Department of Statistics and Operational Research and the Interdisciplinary Mathematics Institute of Universidad Complutense de Madrid. She is PhD in mathematics. She has been university lecturer since 1990, being involved in research projects all along her career, especially in knowledge and technology transferring. Her research area is operational research, in particular stochastic optimization and multi-criteria decision making. Focus on decision aid models for logistics in several sectors like power systems, transportation, disaster management, and sustainable development. Begoña is the head of the University Complutense of Madrid Research Group in Decision Aid Models for Logistics and Disaster Management, and currently she is Associate Editor of Operation Research Spectrum and the President of the Society of Statistics and Operational Research. Thank you very much.
Thank you, Maria. Good morning, everybody. Thank you, Maria, for inviting me and to BCAM for receiving me here. Well, I'm going to talk about decision aid models and data science for prevention and mitigation of wildfires. In our group, we have two main lines of applications of operations research. It's in wildfires and humanitarian logistics. It means humanitarian logistics is for after earthquakes and preparedness and so on, so before. But today I'm going to talk about wildfires. So it's operation research, it's decision aid models. It means that we focus on decision making to improve the preparation or the response for wildfires. So we are currently working in a PhD for response, but today I'm going to talk about two PhDs, Javier León and Adam Rodriguez, that they make the PhD in the prevention and mitigation. So I'm going to explain and present the work. Sí, sí. Tampoco. Okay, yeah. Okay, so this are the contents that I'm going to explain briefly. Well, previously I have to explain that in disaster management is a cycle of disaster management in which disaster management is not only when you respond to a disaster, but it's a cycle that you are working all time for prevention, mitigation, and response. It means we begin. Oh, sorry. Oops. Sí. It means before the disaster, we have a lot of work on mitigation and preparedness. No se consigue.
No, espera, no toques nada de esto.
No, no estoy tocando. No lo estoy tocando. Porque se mueve el ratón.
Espera.
Sí, se había apretado algo todo el tiempo y se ha hecho.
Los cerramos si no les... Igual no va nada. Se me ha quedado. He ido cambiando de algo. No, es que se ha quedado aquí.
Ahí sí, pero no va, ¿no? Bueno.
Aquí delante. Ahí, apretando, ¿qué es lo que me ha pasado? Que yo quería.
Yo nunca he estado.
No, sí. Sí, pero se queda acordado.
Como que no estuviera.
Y pues eso, pues utilizando algunas cosas como para resolverlo de forma. Pasa que según va avanzando la cosa, al final es más rápido.
What? No worries, it's an emergency. We are talking about disaster management, so no problem. So we can improvise. No problem. Okay, I was saying that it's a cycle in which before a disaster strikes an area, you have been working on mitigation and prevention. They try to minimize the consequences of a disaster if it will happen, or to avoid that a threat or a hazard is going to be a disaster. This is prevention and mitigation. Preparedness is when you prepare people, resources, and so on. When the disaster strikes the area, you have the resources and so on for the response. And this is preparedness. Response is the immediate response for a disaster. Sometimes even before, in the emergency phase, when it is beginning, you put in alert all the resources for disaster response. And later recovery, try to recover to the population and putting the people in something similar to normality. It means it's a recovery. There is another one that I used to say that is evaluation, because it's very important to make an evaluation at the end after the recovery phase or after the response phase to know what was working properly, what not, in order to improve the mitigation and prevention and make some changes and activities for mitigation and prevention. So it's a cycle. It's not finishing, never finishes. It's always you are all preparing or doing something to minimize the consequence and so on, or respond on recovery. It's a cycle that never finishes. So in this kind of disasters, wildfire is a kind of disaster. Usually hazards and disasters, they are classified in natural events or technical or complex emergencies. So there are different kind of this classification. Wildfires is difficult to know where to classify because usually the origin of a wildfire is human. So you can work a lot with the people to reduce the hazard. You can work with the people because with the human behavior, education, and so on, because the origin is mainly for people. The typical one with electricity and a storm and so on is not so usual. That is the beginning of a wildfire. Usually, it's the people. Sometimes because they want to put the fire, but sometimes it's only negligence. It means I was burning some rest of the things, and suddenly there was a fire because it was very dry, or something like this. So the origin usually is human, but the spread, the propagation, and the consequence is natural because the fire is advancing and the spread is spreading in the natural, in the environment. So it's a mix. It's a kind of the disaster that is a mix It's a mix. For prevention, you can work a lot with people, for the human behavior, but for the consequence and response and so on, you have to work with the environment, with something as a natural disaster. It's a mix, okay? So, and for prevention mitigation, how can we can work for prevention mitigation of wildfires? Well, I was saying in educational, working with the population and so on is an option. But also there are something that's technical, and especially modifying the fuel load in the landscape. This kind of modification mainly are made with prescribed burnings. It means you can make a controlled burning in some areas to reduce the full load. It means all the rest of leaves and so on. I don't know how it is in English, pinocha. This is the kind of leaves of the pines that they are very good for wildfires. So when you make a controlled burning, you can reduce all this material that is easy for fire and make it spread easier. So one way is to burn in control burning. In some countries, it's very typical and is the usual because there are big extensions of forests. For instance, Australia. In Australia, it's normal to make this prescribed burning like reducing the Another way is not cleaning a complete areas, but doing firebreaks. Firebreaks, usually, we have the idea, when at least I had the idea before working in this area, I had the idea that firebreaks is what of spread, and to make easier to people fighting against fire working in the firebreaks. The landscape. Van a reiniciar todo, qué pena. Yo creo que todo es porque he presentado yo un botón de más.
Se ha bloqueado.
Okay. Or anything else. Or if you are working in this area, burning and so on. Okay. Yeah.
No sé. Vale, no sé en cuál estás ahora.
Ni yo porque... Voy a ver si estoy viendo. Okay. Yeah. Well, and so the representation, as I say, is that we are going to parcel the landscape and working on burning here or not burning, or if it's a firebreak, disconnecting two nodes. Well, you can see here. For instance, a kind of firebreaks. This is in Corsica. We were in a European project. It was a Marie Curie Rice Action. It was Joseph, and we worked with the firefighters of Corsica. And Corsica, for instance, the way to fighting disasters is doing the SAL. So después a la lutte, in French. Okay. So there are some areas that you clean here, and so you have a small vegetation. You can see that here is out of the firebreak, but they are big firebreaks, making with a way in the middle for the access firefighters when there is a fire, and with some water reservoir. Okay? Well, so, hola. No. No. No.
Begoña, déjame.
Ya.
Ya está. Tienes que. No le toques al arriba porque creo que cambia el formato.
Well, okay, we can see here on fire. It's suppose that we have one firebreak here. That there is a road in the middle, okay, and there is a fire here. It's a real fire that happened in 2011, and this is the hour, and this is the wind direction. So a fire ignition is here. So this is the sequence of how the fire spread and how people work on the firebreaks to stop fire going over there. You suppose that in this area here there is a camping and so on. As in summer, Corsica is very touristic place, very nice place also. So this is the fire. Okay. You can see the wind. The wind is changing wind direction. Okay. So it continues here, with different pictures here. One thing important is, Yanni, we were talking yesterday. It was about the jumps that fire is doing, and sometimes you can have here people, but the fire jump. Usually we are not assuming this fire behavior, but it's real fire behavior. It's the most dangerous because sometimes people is working here, and fire begin in the back. So sometimes you are still in the middle of fire. Okay. So this is how changing the landscape, modifying the landscape, you can make easier the access of people to fight. Okay, this is well, here is finishing the fire. At the end, is supposed that it was a burn area, and it's supposed with a simulator, if they don't work here, it's supposed that all this area would be burned. Suppose that they had stopped the spread. So, okay, so we are working in this problem. As I told you, we can represent to work. Sensible, eh? Sensible. Oh. Okay, so I was saying that here we have the landscape, and we have the different polygons refer to the landscape and the things that we have here, and the network approach with nodes and links, direct edge, representing potential fire spread. Okay, so we have developed two models for deciding where to act, where to work for changing, modifying the landscape for prescribed and fire breaks. In the first one, in the model description one, is non-probabilistic. We work in a model non-probabilistic. Well, a thing that is difficult in these models is to introduce the parameters, the data of the models. The probabilistic models we are going to see later, they need the probability of ignition and probably the expressed probabilities, and this is not so easy to estimate. So in Australia, we worked with John Hernan, that his approach is we are not going to do a model based on probabilities of ignition or spread, but we are going to do a model based on the vegetation age. The problem is that when the vegetation is very old, they're more flammable. and it's easier the ignition and the spread. And so we use as a proxy of the risk the vegetation age of each area, yeah? And also we understand that if this is old and this is old, this is a risk connection, very risk connection, because the spread would be very easy. Okay, so we use this in this model. We will use this proxy. And so in each polygon, we have a vegetation age, and as a proxy, we have the high fuel load units, is a proxy of ignition risk, and high risk connections, a proxy of spread. So the objective, it would be minimizing, especially the number, not only the number, the length of high risk connection. Okay. But also, we have a problem that is prescribed burn, and as I told you, in Australia is very common. Prescribed burn is very aggressive with fauna and with the environment. It means it's good for cleaning and to reduce vegetation age and so on, but this is good for fires, but it's not good for fauna, usually. This means animals, they like some kind of vegetation being short or big or and so on, and it's different depending on the animals. It means it's different for some kind of mouses. And I think it is protected like a very small mouse in Australia, but it's different for birds. They like in a different age the vegetation. So usually it is represented, the habitat quality is represented by a fire response curve, but it's different for each animal in the fauna. Of course, no, it's not so normal to take into account all the animals, all fauna, but some special fauna, especially if they are protected, should be taken into account. So we have a model. We have a model okay, that we have these several objectives. Have minimize the high fuel load connections, this high risk connection, minimize high fuel load units, and maximize habitat quality for a number of species. Okay. Which are the constraints? Well, we have a constraint, very important constraint, that is the capacity for performing prescribed burns. Here the problem is that if to develop prescribed burn, you need some weather conditions. It means you have to do it when there is not a high temperature. You have to do it when it's not raining, because if it's raining, you are not going to burn anything. So usually you don't know in advance. The time that you will have for developing these activities of prescribed burn. So we talk this one about the capacity for performing prescribed burn. So the model that we have developed is stochastic, because usually, when you talk with firefighters, they say, well, we say that we can burn around, I don't know, 15 hectares. Around 15. Yeah, some years 10, some years 20, something like this. So we represent this uncertainty in the model, developing a stochastic model. A stochastic model with non-anticipativity. Non-anticipativity not only to the future, but also during the year that you are working. Because you prepare to say, okay, we begin working on these parcels, for instance. We are going to burn this one and this one. If weather gives us the opportunity, we are following with this one. If weather is, we are following with this one. So you have to make it that the solution or your model when you have more capacity, they have to include the solution with less capacity. Okay, it's increasing. So we have a kind of partial order between the solutions. And we have developed a multi-objective stochastic programming model with risk aversion. Risk aversion, it means we are not working with the average, because then the average depending on the distribution of this random variable, but we are working with the worst scenarios. It means we are tending that the worst scenario to be not so worst, or minimize the worst that the worst scenario are, okay? But also because we have several objectives, if we work in this same idea with the objectives. So the worst objective function not to be so worse, it means. So we have developed a model based on the CVAR, conditional value at risk, and OWA for the ordered weighting average for multi-criteria. The idea is more or less the same one, so in stochastic or multi-criteria, if you know which is the conditional value at risk, but if you don't know, imagine that you have, this is the distribution of the values of your objective function, okay? It's stochastic, different values, and we can imagine that the worst is the higher. So value at risk, you know, is a percentile. Percentile here, for instance, the 5%. It means that the 5% worst values are here, and the conditional value at risk is the average inside this part. Which is a difference in the CVAR and VAR. VAR needs binary variables for representing, CVAR doesn't need. You can do it in a linear way without binary variables. It means the model has binary variables, it is not changing, but the representing the CVAR don't need to introduce binary variables. So we are using this one for the stochastic part, and in the sense for OWA, if you have here the values of the different objective function, okay, you take those ones that these worst objectives, and we also minimize the conditional value in this part. We have to suppose that objectives have different weights, different importance presented. So, okay. So in this case, we have a model with some parameters. You can see here that we are not using probabilities except for the capacities. Okay, it's a model that we use here. Initial fuel age, bias for full treatment, the area. So interval of age for varying unit. Suppose that maximum of age and minimum age should be half. This is for the fire response curve, that is piecewise linear, but not it's not increasing all time. Okay, and the probabilities is only for the scenarios about the capacity. Okay, so the variables are basically is if we are going to try to burn this node or this area or not, but also which year, because we must take into account the future for our decisions here. It means I'm going to burn here and here, and I cannot consider that it's finished, because next year I will continue and I will burn other areas and so on. So this is an evolution, so you have to include planning for several years. For several years, it means that it's forest. The years for forests are long, so the planning is including 5, 10, 15 years for future to make decisions today. Okay. So the variables we are representing, as I told you, this is the scenario 3. Okay. Here we have to make the decision here, and with different capacities for developing the prescribed bar, we will finish with different ages in the in the landscape after 1 year. But this continue in order to take into account for making decisions today, the future. And this is that we cannot work, or it's limited. What can we work with some kind of capacity, and this is the idea that with more capacity you have to include the previous one and also other news. Okay, I'm going to. Okay, this is the formulation, the Sebar and Owa. That is written in an article with Javi León. Javier León is the PhD student that finished their PhD in 2020, working with Justo Puerto from Sevilla University. And this is the formulation for Sebar and Owa. Is you can see is everything is linear, no binary variables. Okay, but also you have to include here the constraints of your model. In our model, there are binary variables. This is not changing; it's maintained. But we not include more complexity to the model. Maybe this one. Okay. Yeah. We have applied this model for a case study in Andalusia, in Sierra de los Filabres, for prescribed barb, and this is the area of Sierra de los Filabres in Almería. It's more or less big. In Spain, it would be a big area. In other places, Australia, United States, and so on, is small. But in Spain it's more or less big, and is divided in 193 units. Okay, this is the landscape. This is the landscape. We can see, I don't know if you can see different colors. It's supposed to be different, as I said, not the flammable, but it's like the vegetation, I think that kind of vegetation. But here you can see the owners. It means this yellow that is protected, you cannot make a prescribed barb in there. And in the private areas also, you can do it. This is a limitation, an important limitation in landscape and fuel management. That private, you cannot make actions for prevention in private areas. The owners should do it, and the politicians should make some promotion between private owners to make the same kind of work that we can make in the public areas. But actually, if they don't want, nothing is done in the private areas. So when you can work is in the blue. This is the area that actually you can work, but you can take into account all the areas because they make easier the spread and so on. So in the model they must be included. So time horizon for this case is 5 years. We know that it's not so much. It's a little bit small. In the case of the previous one, that it was not a stochastic, it was not with a mixed aversion. We worked with a rolling horizon base in order to include until 25 years of polystyrene. But also, okay. Also a difference in Spain with Australia is that in Spain it's not burned all the area. When you make prescribed burned, not all the parcel is burned, usually only 15% more or less, because they burn this part mainly. Why? Why? Because there is no capacity to make more. Basically, if you don't have the time, you don't have the means, the resources to do it, so you have to go to the most important thing in this case is cutting the connection between the cells. Okay, so the model. We consider also two species. I don't remember which one. Sorry. Two species. One that likes more young vegetation, and other is not so young. But all of them, after some years, with all vegetation, they don't like it also. Okay. So these are our results, computational results. Yeah. Is supposed with different for the Sebaranova is here what probability we are considering here, and we are working with big values because we didn't have so many scenarios, and also for the objective functions with the weights of 0.25 and 0.5. So these are the computing results. If you minimize the average, no risk aversion, okay, you can see that the minimum value is 0.2, and for the tails, with if 0.5, 0.5, these are the values. Each line is representing the optimal one. If we are optimizing this one or this, it means, and you can see the value, the rest of the for this optimization. It means this is the optimal, the optimal, the optimal, the optimal, and the optimal. But we can see, for instance, that the average, when the objective function is one of this one, the average, of course, is being worse, but not so much. But, for instance, if you optimize the average and you are working, for instance, with this, you can see that there's a big difference in the tails. So if you are you have risk aversion, and in the worst cases, you consider the worst cases, what you're doing, you should consider one of these values to put in the objective function, because the average minimize the importance of the tails of what's happening in the worst cases. Yeah, the average could be very good, but the worst case is not. And you can say to the decision maker, "Oh, the scenario is one of these worst cases," and to say, "Oh, my model was very good for the average, not for this one." So it should be very important to take into account what are you doing with your decision making, because afterwards one of the cases is going to happen. So you should control what is happening in the worst cases, because it can be the reality. Okay. Well, we have here the solution for the model, and you can see this is the original ages of the units. So remember that we can work on the public areas, that it was a moment. Public areas are these blues, not around, and this is protected. So in the solution, this is the age, as more yellow and so on is older. So we can see this is the origin, and with the less capacity, you are going to burn these points, these areas. It's corresponding to this part of here. It's normal, because it's the oldest all these areas. If you have more capacity, you increase this area burning this one, and you have more increase from this one burning here. Okay, this is the solution. It's supposed that the future is also represented, but the future is not the decision making. You are making decisions for this year, and next year, after doing, you don't know if this one, or this one, and after fires during the summer, you will have another situation with another age, and you will repeat decision making. Means you take into account for making decisions, but it's not a plan for the 4 years because you have to repeat when the reality is revealed. Okay. Well, this is a model that is good for terrestrial burn and is more or less good for big areas and so on. And it's very good because you don't need parameters, some difficult parameters to estimate, like probabilities and so on. But the reality is that you can develop also a model, probabilistic model, including these probabilities, probabilities of ignition, and probability of spread. So you can measure the risk of a landscape with these probabilities, and so make decisions changing something in the landscape and measuring how the risk is changing. So we have developed a model, probabilistic also, is another thesis, it's Adam. The previous one it was Javier, and this one is Adam. They finished in 2020 and Adam in 2021. So this is a probabilistic model in which we define the risk, like the value of these parcels, the average. It says the value of these parcels times probability of burn each of these areas with this landscape that we have. This is the probability that this parcel of this cell is going to burn in the next years. Okay. So, but how to estimate? Problem is how we are going to estimate the probability of the event node I burns. It means it's not so easy. So, firstly, we have to make some assumptions. And the first one is that we are going to make the assumption that a parcel cannot burn twice in our period. It means that we have to reduce our planning horizon for a few years, because a parcel can burn this year and in 10 years burn again, because it's a new vegetation and so on. So we have to limit our study for some years. 1, 2 years, 3, until like this. The second assumption is that ignition and fire spread capacity between nodes are independent. You have to understand. Ignition is that the fire begins here. Spread is that it's moving from here to here. But, of course, spread should, we have a spread only if there is a fire. But the capacity that in case there's a fire is here, spread from one to another, doesn't need that we have a fire here. This is that we consider independent. It's independent, the probability, the event ignition here is independent when it's possible to transmit a fire from a node to another one, in case of a fire right here. Well, with these assumptions, we make these models, and we say how to calculate. Imagine that we have the ignition probabilities in each node. It means we don't have a fire. We are talking about in 2 years. Imagine that once, which is the probability that once there is a fire ignition here. This is more or less difficult, but not so much. We can work with historical data, statistics, and so on. And a capacity to spread is not so easy. the probability for transmit a fire in case of arriving. It's not so easy. We work with also with historical data and also with physics models, like Gianni is working, I think so, in physical and statistics models to transmit from one node to another one. But even so, with this data, we can compute the probability of a node burning. Well, the first thing we see is that we could define the fire, the event, in a recursive way. In a recursive way in which the event fire in the node I could be ignition in the node or arriving the fire from the neighborhood, okay, or we can define it ignition or arriving the fire from ignition on other part of the network. It could be equivalent, but we have the proof that not. They are not equivalent if the network have some cycles. So we have proved that, for instance, for this simple network, the solution, some diagrams, could be this one or could be this one. Both are solutions for a simple network like this one. So, in order to use this more simple expression, we have to work with direct acyclic graphs. In this case, it's equivalent, and we can work in a recursive way. Moreover, as a Bayesian network, and solve the problem of the probabilities with the algorithm for a Bayesian network. So, to solve the problem, we have to estimate the probabilities of ignitions and spread, and decompose the graph in several directed acyclic graph, in which each of them can be solved with Bayesian networks. But this is made more or less automatically. It's not a problem. The other problem is that it's not a problem when we have the wind direction, but we have a problem when there is not wind direction. Why? If we are solving the problem for 2 years, 3 years, it's supposed that when we are doing the Bayesian network, that fire is going in a direction, but we don't have this one. So we have to make scenarios on wind direction in order to have the directed acyclic graph. Okay, so we develop scenarios in order to the welfare rights measure be the probability of these scenarios of wind direction with the probability of burn in each of them. How to develop these models? These scenarios is not so easy also. Sierra de los Filabres again. It's the same case study. And we have represented the scenarios, wind scenarios like this in some cells, and studying historical data, wind scenarios, and putting for each of them the direction. Okay. Well, the first thing is that if you take the wind direction, this is component 1 and 2, from 20 years, each 6 hours, you have here a thing that is not showing any special form, but we have filtered by risky days, and understanding risky days is over some temperature, low humidity, and now there is a kind of shape in order to make scenarios to represent this the wind direction. Understand that wind direction is at one point here. We have the x and y direction. So using a multivariate Gaussian model, we could have this model for the density with the likelihood ratio test it's decided that 11 is the number of scenarios that should make to represent the different wind directions. And here are the scenarios. The different scenarios, the color is the intensity, yeah? And we can see the arrows with the direction. The 11 scenarios that we have developed to represent the wind direction in the 20 years. Okay? And with these scenarios, and also using physics models, the Rothermel is a classical physics model to represent the intensity and also the political spread depending on intensity and so on. And so we arrive to our case study, in which the methodology, firstly, we determine the propagation spread scenarios, wind direction and intensities. Okay, we estimate, well, the probability of ignition based on the scenario and the kilometers and type of road crossing the area, because it's known that it's very important. Usually ignitions begin close to roads and ways in places that it's easy to access for people, because as I told you, mainly the origin of wildfires is human behavior. So when it's close to, when the people can arrive, it's more easy. There is more risk for ignitions. And we estimate also the spread with the wind speed and direction in the scenarios. Later, we rescale some of the probabilities to fit the observed historical data. It means that we work with this probability of ignition is the origin, the estimated, but with some value, or lambda, in order to fit the historical data and also with the number of fires, and in this one, and we apply the model to estimate the fire risk, and we obtain, this is the different values, different probabilities of burning, and the different cells in the Sierra de los Filabres, and we have a value for the fire risk. Okay, the model itself is not decision making, because it's only the value of the expected value, okay, of the risk of the landscape. But suppose that we can, with this value, we can work and say, for instance, okay, I'm going to burn in this area. I'm going to burn, for instance, here. No, it's dangerous. I'm going to burn here. If burning here, so if I change in this one, the ignition probability is lower, and also the spread through this cell. So it's changing the fire risk. So what are we working now is including in a optimization model this methodology as the objective function. So we have to decide when modifying the landscape for minimizing the risk of the landscape. It's not easy, because you have to make a call outside, go to the Bayesian networks and so on to receive the value of the fire risk. So it's absolutely non-linear. It's not difficult, it's an abstract problem, but with an objective function that you have to call to an external function to obtain the value of the objective function. So we have to do some kind of heuristics, and we are working now to include this model as the objective function. Okay, so this is the conclusions, and nothing special. It's the summary that we have for prescribed and not using probabilities. That is very easy. It's very difficult to estimate, actually. So we are working, especially for big landscapes, we are working with a model that is not probabilistic. It's a stochastic, but on the possibility for actuate. And the other model is a probabilistic model is more for the shorter term and is better for full breaks than for prescribed burn, because prescribed burn affect very hardly to the landscape. So you should take into account the future. Firebreaks is not so aggressive, so you can work more in shorter terms. And we're working on optimization. Okay. These are the risk aversion approach for the multi-objective, and we have the results in safety science here. And the model for the fire risk for decision making is here, and the application is forthcoming. We are trying to write the articles. All this work was developed in a geosafe project with the Royal Melbourne Institute of Technology in FOCA, it's Andalusia, firefighters and so on. And I have not written, but the basis of our knowledge was given by the firefighters, of course. So.
Thank you very much, Begoña. I'm sorry for the technical problems. We have some minutes for questions. You want to ask something?
In the first model, you said that there are some areas that you cannot burn, like preventive burns, but do they have the same importance in the objective function? I mean, it's not the same burning the...
No. The way to work with the area. Are you talking about the importance of the different cells in the objective function when you burn or so on? We take into account the area that you are going to burn, and for the connections, the length of the links.
But I mean, it's not the same when the wildfire occurs. It's not like the same having the protective area burned or the public one or the private. I mean, you said like you cannot burn like preventive. No?
The problem is this one. We only can work for decision making, when to work. We only can work in the blue one.
Yes.
Only the blue one. The green and the yellow are not allowed to work on this. But they are taken into account for a spread, because they can make ignition here, ignition can begin here. They can spread can be from here to here. We are limited by the owner. So
but
the question is?
Yeah, the question is, do you try to protect in some way the yellow area or the other ones, like they're more important than the other one?
No, actually. Not actually, we are not doing it because we're only working on, we are not penalizing, for instance, more this area because we are working on vegetation age. So we are not working on it, but it could be good to include it. Yeah. Yeah, it could be an idea for including some kind of trying to protect some areas, especially some areas like this protected, this one. Usually these protected areas is because there is some kind of fauna that, or flora, or fauna, that nature that you have to protect especially. Sometimes it's not clear what is protected, because sometimes you are protecting for not burning, not touching, and fauna and flora, they don't like their own vegetation, but it's supposed that we are protecting, but it's a good idea to include it. Okay.
We have a question from San Sebastián.
Ah, yeah?
It's a question from José Antonio Lozano, and the question is, how do you learn the Bayesian network? The second.
How we solve it? How do you learn? How do you learn? The Bayesian network, because we are including directly the probabilities, is actually we have not to make the learning of inferring the probabilities and so on from data. We include directly the probabilities, and we have It means a Bayesian network, but it could be, also solved with other models like models of cascade for network, social networks. Okay, but we are not learning because we have the probabilities explicitly given as parameters. So we are not learning in the training the Bayesian network. We use only the algorithms used to solve Bayesian networks being applied for obtaining the values for burning. But we don't have to learn that the Bayesian network have to learn which are the probabilities from data. We are including directly the probabilities of the networks. It means, for instance, that if you are assuming that one direction is like this, so for instance like this, so you can say, okay, this it could be ignition, and we have a probability of ignition. So from here it can be to here, maybe if you do it like this, to here. And so, but we have the probability of ignition here and probability of spread. Yeah. It's a Bayesian network, the algorithm, because it's easy to use it, but it could be pure probability calculus, because it's always this one burning here is depending on this one. So with it's not needed training. Training the network is not needed. It's only applying the algorithm to solve it with the probabilities. I don't know if Jose is happy with my answer. Yeah, it's okay.
Do you have more questions here?
Just a precision. So the DAGs you are using mean that, for example, if the fire starts in one corner, the first node of the DAG of the map, it may spread to the whole map. However, if it starts, for example, in the opposite corner, so the end of the DAG, it will spread nowhere. It's what it means, right? Okay.
Yes. It means that one is one direction is that is allowed to say that the fire can be potentially can move from here. If we don't make assumptions on one direction, can be also from here to here, and this is a cycle, and there is no solution with the algorithm Bayesian networks. It's not very well defined, as I told you, in the sense of the recursive way. This is that we prove here. That if you use this one and you can go from here and from here with different probabilities, this is solution, but also this is solution. So it's not well defined like a recursive from the neighbor. It's well defined from the ignition in all of the rest, but it's not Bayesian and it's difficult to do. Okay, so in order to use this one, and this is to use the algorithm for Bayesian networks or Bayesian theorem. Bayesian theorem. Okay, in order to use this one, we have to eliminate the cycles in the graph.
Do we have the time for another question or
Yes,
not?
yes, of course.
Very general, is there a way precisely to deal with retroactions in causal graphs, or is there a way to formulate and easily elucidate cycles precisely?
Well, after doing after doing the scenarios, you change and you broke a lot of cycles, but not all of them. But also there are in Bayesian networks there are some algorithms or methodologies to separate into networks that they are a cycle.
Okay. So
And later join it for the solution.
Oh.
It's a methodology. Adam was working in this and he programmed very pretty well. the methodology to separate in different, even in the same scenario, but separated different, solving this one and joining the solution later.
Okay, thank you.
In the first model, how many scenarios do you use?
We were working on only in 3 scenarios, but it could be more. Probably this first model is susceptible of improving, maybe taking into account the idea of Imanol, and also increasing the number of scenarios in order, because this first decision is clearly a plan. So you should have the plan clear of more capacity, we are increasing. And you should increase the number of scenarios. And also take into account more years in the future. Before being a stochastic and risk aversion, we were working with 25 years of years for planning. But in order to solve the model in more or less short time, more or less, with only 3 scenarios of 5 years, it should be improved, but probably with some methods, the composition methods or anything else for solving.
Okay, thank you. Well, do you have more questions?
Well, just a detail. These 2 formulas, the discussions of these 2 formulas is published where?
Of this model, no? The second model, we have this theory.
Comparison. Okay. The discussion that these 2 formulas, one is well defined and the other one is not well defined, is part in a paper.
Yeah. Yep. This one.
Rodriguez Martinez.
Here is discussed why there are 2 solutions. It's not well defined when they are improving the neighbors, if there are cycles and so on. It's true here that when you change the cycles, it's equivalent and you can use the network. It means is that if you don't do it from the neighborhood, you can use that burning here is depending on fire here. You need all the ignition. So we have to change the cycle and the spread and so on, separating in order to use the classical use of Bayesian models and Bayesian models.
Yes. So we will thank you again, Begoña. Thank you very much.